Hi, everybody. This is going to be chapter 36.6. We're going to talk about diffraction by a circular aperture. And the angle, the sine theta for the first minimum around that circle is given by the expression of 1.22 lambda over d. That is a typical diffraction value for a circular aperture. It is different than a single slit, which has a simple first minimum of sine theta is equal to lambda over a. And this is an important limitation. It is a physical limitation that all wavelengths of light have whenever they're going through a circular opening. You can think of circular openings like the pupil of your eye, the camera lens that you have on your phone, a telescope. Anytime light is going to go through a circular opening, this is going to be the essential limit as to how effectively you can see distant objects and resolve them clearly. So when we're talking about different objects, particularly astronomical objects, we want to have a way to identify when we can separate two images that are far away and clearly distinguish the two of them. So this is known as the Rayleigh criterion, and that is the idea that for small angles, sine theta is approximately equal to theta, and so we can set theta is equal to 1.22 times lambda over d, where d is the distance to the object, 1.22 lambda over d, where d is the diameter of the observing location, either your pupil of your eye, the opening of the camera, or the opening of your telescope. That is the that's what that is. So if I have two light sources that are so close together that the angle between them is smaller than this 1.22 lambda over d, they end up being unresolved. And we know this will happen when the peak of either one of them is inside of the first minima of the other one. Therefore, we do not see resolution. But we do hit the Rayleigh criterion when the vertical peak of one of those hits the minima of the other one or is just past the minima. So that is just the instant when the two images are resolvable. And if you get a little beyond that, then it's much clearer. And they're very well resolved when the peaks are far away from the first minima. So that's the idea of a Rayleigh criterion. Another item to think about, you can estimate whether or not you can see something clearly by taking the arc length, meaning that the distance between 2 points, if I were to look at two stars and ask the distance between this point on this image and the distance to this point on this image, would I be able to see these as clearly resolved with a camera or a telescope of a certain size? I would be able to identify this utilizing this equation. S being the arc length, the separation between the two objects, is equal to r theta, where r is the distance to the objects you're looking at, and theta is the angle between them. And so you'd be able to resolve r is 1.22 lambda over d, would give you whether or not you can see the separation between different objects. So this is an important thing when we're dealing with astronomical situations, but there are other real-world examples as well. We'll go through a couple of them. So, an astronomical, what is the theoretical minimum angular separation of two stars that can just be resolved by, for instance, a 200-inch telescope on Palomar Mountain, when you're looking with a 550 nanometer wavelength, which is roughly a green-yellow wavelength. And the other one is then the Arecibo radio telescope, which is in Puerto Rico. That has a diameter of 300 meters and is typically used for radio wavelengths on the order of 4 centimeters. So the first part, we're looking for quite simply what is the minimum angular separation. Well, the angle is 1.22 lambda, which is our wavelength, divided by d, which is the size of the 200-inch telescope, and we get a simple measurement of 1.3 times 10 to the minus 7 radians. Make sure when you're doing this, you're keeping your units correct. They should cancel out, and you should get a unitless value of radians. Now, if I do this again for the Arecibo radio telescope, I have a 1.22 times 0.04 meters divided by 300, and I get a 1.36 times 10 to the negative 4. So it's very clear that with a much smaller telescope and visible light, we get a much better angular resolution in part A than we would with part B, the radio telescope. Resolutions with radio telescopes are nowhere near as precise, but they do provide us with significant useful information. This is what the Arecibo radio telescope looks like. Anybody who's seen a James Bond film, you will have observed James wandering through here. This was one of the evil lairs, which turns out to be a scientific facility. But they're very, very large because of the fact that radio waves are quite long and you need a very large dish in order to focus those rays and get a good resolved image. Another example of this, supposing you're in an airplane, you're 10,000 feet off the ground or 10,000 meters, and you look down at the ground and you want to know whether or not you could count cars in a parking lot. So you're going to estimate that minimum separation between objects and ask this question. Now, how big is a car? Typically, they're about 2 meters wide and somewhere between 3 and 4 meters long, depending on whether you're driving a small car like a Saturn or a big car like an old-style Cadillac or Crown Victoria. So, can you count those cars in the parking lot? Considering only the diffraction, assume your pupil is your capital D diameter of 3 millimeters, and you're looking in the the green-yellow wavelength of 550. We'll do it again. So now R is your distance, that's 10,000 meters, and your Rayleigh criterion angle, 1.22, and you see that you can see the difference between objects that are 2.2 meters wide. And that means you could resolve the cars just enough to count them in a parking lot using just your eyes. The book example gives a representation of this pointillistic painting by Maximilian Luce, and it's basically made up of thousands of dots, and they are providing you with an example where you're determining the Rayleigh criterion by which you could observe the separation between different blobs of paint, but effectively it's the same problem we just did. So take a look at this and see what you think, and I will stop here for the diffraction through a circular opening.